Hi, Kiran and Nandkumar. It's 6, but it's just the three of us here. So we'll wait for a few more minutes to allow more people to join. Thank you.
Yep.
Good evening, and welcome to week two of the live sessions for the fundamentals of additive manufacturing technologies. I am Sourav Goswami. I am a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. This course is taught by Professor Sajjan Kapil, who is a faculty in the Department of Mechanical Engineering at IIT Guwahati. Last week, we looked at we were introduced to additive manufacturing terminology, and we got an overview of all the basic processes. Also, we started looking into how uh, the exact geometry of a solid is converted to STL files, how the representation is always an approximate representation, but with smaller triangles and finer mesh sizes, it tends to the exact approximation. Okay, that's an oxymoron. It tends towards the exact shape and geometry of the solid, but for all practical purposes, it will always remain an approximation. And given that it is an approximation, there will be certain deviations from the exact geometry, and we'll do a couple of numericals on it, which were pending from the previous session. The first one suggests that there is a requirement for the number of triangles to be found, which will produce a deviation tolerance of 0.01 mm while representing a circle of 10 mm radius in a file of STL format. The formula for this was already shared in the slides, so I'll directly reproduce it. And if we go about it, say you have a circle and you are tessellating it or dividing it into triangles. So this is just an approximate representation of the same. And say you have the radius of the circle. So you know the value of r, which is 10 mm, and you're required to find the deviation tolerance. The deviation tolerance being the maximum perpendicular distance between the actual geometry and the STL representation. So in this case, this chord height would be representative of the deviation tolerance. And say you have that you have used to tessellate this circle in your STL file. Now, for n triangles, if each of these angles is some theta, then this theta is 2 pi by n, because assuming, of course, that all triangles are congruent or identical. And then we already have the formula for the deviation tolerance d, which equals r minus r cos theta, r being the radius of the circle, d being the deviation tolerance, which is equal to r times 1 minus cos theta, and in this case cos 2 pi by n. Now we also have the value for d, which in this case is 0.01 mm. So 0.01 to the radius is also in the same units, mm, 10 times 1 minus cos 2 pi by n, which implies that 1 minus cos of 2 pi by n is equal to 0.001 cos of 2 pi by n, and out to be 0.999. And if you do a cos inverse of that, so Okay, I made a mistake here. So the formula involves theta by 2. So I'll just erase it. This will be pi by n. Pi by n will equal cos inverse of 0.999, which is actually 0.0447, and this will give us a value of n equal to exactly 7.28. But given that n here should be a whole number as it is representing the number of triangles that are needed, we'll take the next higher number. So the number of triangles needed in this case is 71. Just like this was a geometric or a deviation tolerance, we also have a numerical on how many triangles will be required for angle tolerance to be zero point 0.2 degrees to represent a cylinder of 100 mm radius by STL format. And I would just like to give a recap of what angle tolerance was. So, say this is some curve that is being represented, and these are the edges of two consecutive triangles. Then they would have these normals, and the angle that is made or that is contained within these two normals is called the angle tolerance. So, in this case, again, the formula was shared in the slides. We'll get directly to it. So, let there be n triangles that are used to tessellate this cylinder. Then we have 2 pi by n is zero point 0.2, or we can also do in degrees. So 360 by n is zero point 0.2, or therefore n is equal to 1800. But this would only be 1800 triangles for the top surface. But for the case of a cylinder, we know that there is a top face, there is there are these lateral sides, and then there is this bottom face. And as Professor Kapil discussed in his lecture, each triangle on the top or bottom face actually corresponds to two triangles on the sides. Thus, the total number of triangles that will actually be needed to tessellate the whole cylinder will equal 1800 for the top face, 1800 for the bottom face, and 2 into 1800 for the lateral face. I'll also write that here. This is for the top face, this is for the bottom face, this is for the lateral surface. And I'm getting into for 7200 triangles. That is the solution for this question. Now we'll get started for the content covered in this week. So as usual, our modus operandi will be to first have a quick run through of the concepts that were discussed in this week, and then solve a few illustrative problems to further test our concepts and maybe even help you to solve your assignment problems better. So in this week, we continued with the discussion of manipulation of STL files. Previously, we saw how any geometry can be approximated by tessellation, usually with triangles, into an STL file format. Once we have that approximation, you would like to manipulate it, say rotate it, translate it, stretch it, shear it, and so on. Slice it, most importantly. And thus we should know what goes into the background of such operations. So we'll be briefly looking at rotation, translation, and the types of support structures when support structures are needed, what zones they might be required in, judging from a qualitative perspective. And then we'll also see what are some of the optimal part orientation models that are implemented in commercial software. As most of us would be aware, in any mathematical package or in any engineering package, rotation is usually accomplished by matrix multiplication, and here the same has been derived. So for any point demarcated by this blue one here, which had an initial coordinate of y1, z1 in the yz plane, if it is to have pure rotation about the x-axis in this case is coming out of the plane, and say it moves to a second position demarcated by this red dot here with the coordinates y2, z2, then a relationship can be derived between these two positions, where for the second position z2, given that the length of this point from the center remains constant and it is only given pure rotation about the x-axis, can be expressed in terms of y1 and z1 as z2 equals y1 sine theta plus z1 cos theta, theta being the angle by which this point is rotated over the x-axis from its initial position. Similarly, for the y coordinate, y2 equals y1 cos theta minus z1 sin theta. And once you rearrange them, it is easier to make out the matrix form of this transformation. So the coordinates of the new point x2, y2, z2 after a pure rotation by angle theta about the x-axis may be obtained by pre-multiplying the existing coordinates x1, y1, z1 with this multiplication matrix that in this case is referred to as r theta x, and which is simply 1 0 0 0 cos theta minus sin theta and 0 sin theta cos theta. That was the case for the Cartesian coordinate system for pure rotation over the x-axis only, and you may have it is easy possible to derive the same relationships for pure rotations about the other axis. So here we have the rotation matrices for rotation about the x-axis r theta x, for the y-axis r theta y, and for the z-axis r theta z. As one would already be aware, in matrices the multiplication is not commutative, and thus we need to keep track of the order of multiplication in general. So for two matrices A and B, AB will not equal BA. In some cases, it might also not be permissible because the operations may not satisfy the requirement for the number of rows and columns to be equal, as you might know. So if you have a m cross n multiplied to a matrix P of B time of P cross Q dimensions, so in this case, n should be equal to P. These are just a couple of preliminaries we must keep in mind. Thus, when we are rotating a point about three axes by the angles theta x along the x-axis, theta y around the y-axis, and theta z around the z-axis, based on the sequence of rotation that you apply, the final result might be quite different. Say, if in one case you first want to rotate over the y-axis, then the z-axis, and then the x-axis, the final operation would look something like you have this initial point P, then r theta y, r theta z, and r theta x. And this will give you your new point, say P prime. If for a different case, you first want to multiply by x, then rotate it along the z-axis, and finally around the y-axis, your final outcome will look something like r theta x, r theta z, r theta y will give you the new point. Also, in our courses on, say, vector mechanics, we might have been made familiar with the concept that finite rotations do not really add up vectorically, so the sequence matters. Similar is the case here. And the way we reorient or rotate a triangle is to do it point by point. So we perform these matrix multiplication operations for each point as shown here. So pkxi, pkyi, and pkzi are coordinates of the kth vertex, k being from 1 to 3, of the ith triangle. So for each ith triangle, we perform this matrix multiplication operation on each of the three vertices sequentially, and then we end up with a new orientation. In a quite similar and easy fashion, the new orientation of the normal can also be calculated simply by multiplying the components of the normal vector, unit normal vector, with the rotation matrices as necessary. Here we have the case for translation. So I will, for pure translation, you only move the body without giving it any rotation, and you displace it parallel to itself along the x, y, and z directions as needed. The new positions of the points can be obtained simply by adding the displacement matrix x, y, z. And as was well described, pure translation in itself will not change the orientation of the unit normal, and thus the components of the normal vector remain unchanged. Now we move on to the discussion on support structures. We already looked at how support structures are needed when we are depositing materials which might not be supported by any pre-deposited layer or in substrate. Typically, such a region is called an overhang. Do all overhangs require supports? No. If for a given material and machine combination, the overhang is small, it may not require a support after all, but large overhangs in general will require supports. There are certain strategies to mitigate the need for supports or at least minimize it, and we'll be looking at those as well. So, support structures are mainly required while creating or printing overhanging features. In a few AM processes, such as binder jetting and powder bed fusion, explicit support structures may not be required, yet they sometimes are required. But in general, they may not be required because the remaining loose powder can act as a support material. However, in some AM processes, the support structures need to be added and created suitably during the pre-processing stage. So while we are still on our computers, working through the design and generating the final G-code file, which will be printed. The support structure, as we know, is a sacrificial material, and such a sacrificial material can be either made of a different material, typically weaker, or it can have a lower density, or it can have some other properties, say it can be chemically or preferably solute. It can be preferentially soluble in certain chemicals, such as even water, or in cases like FDM, it can be, say, of a different color. And we should be careful that the support structures, while should be strong enough to support the overhanging features, should also be weak enough to be broken away easily during post-processing. And especially care should be taken to ensure that they do not leave artifacts or remnants on the finished surface of the part. Else it would increase the post-processing effort. How do we determine when a support structure is needed? Is it always the case that any overhanging feature will require support? or what is the criteria, general criteria which can be derived. So for a given STL file and for a fixed build direction, the support structure can be easily calculated based on the facet normals of the triangles, because the facet normal in a way is the quantitative indicator of the orientation of the triangle in space. If the build direction is vertical, which is mostly the case for most AM processes, unless we are working with a high degree of freedom machine such as a 5-axis CNC retrofitted with a deposition head, then in most cases, triangles having normal pointing upwards from the horizontal, that is, will not require support structures, whereas normal pointing downwards may require support structures. May, because if this angle of inclination is relatively small, such as here, the support structures may still not be required, whereas in the other case over here, where this angle is far larger, we can safely say that support structures will be needed. Now, for a particular material and machine combination, I'll keep repeating this because these calculations are not generic and will change based on the process, the material. So for a particular, may even change with the machine, so I might as well add that. So for a particular process, machine, material combination, will it change with the process parameters? It just may. I have not tested it. It is possible to find this critical angle of overhang, which would beyond which the support structure will be needed. So let us look at two gross cases. In one case, you have these large overhangs and you have these large layer thicknesses, both denoted by capital letters T and D. And in the other case, you have these finer layers of a smaller thickness, small t, which produce an overhang of a smaller dimension, small d. If such is the case, it is possible to determine the angle theta, which the facet normal in this case, or the exact shape that we're trying to print, makes with the building direction, being positive k or the z direction in this case. That theta comes out to be pi minus tan inverse of t by d. And the criteria which we will follow is that if the angle alpha between the build direction and the normal facet normal of the triangle is greater than this critical angle theta, which we just calculated, the supports will be required. Again, how do you calculate alpha? You simply take a dot product between the build direction and your facet normal. In this case, if the build direction is along the k hat direction, so just the k component survives. Thus, alpha is simply the cos inverse of the z component of the facet normal. We also have a simple example here with direct formula application. So in an AM process where the maximum possible overhang can be 1 mm, this is the value for small d. The build direction is plus z, so again oriented along the k hat direction. The minimum possible layer thickness is root 3 mm, this is the value for small t. Find out the critical value of the z component of the facet normal of the triangle, beyond which the support is required. So we first find the critical angle theta, which demarcates the transition from a no support to a support required regime. This theta is pi minus tan inverse t by d, which is here shown as 180-degree minus tan inverse root 3 by 1, or 120 degrees. And what this means is here this is our build direction, and say you have multiple at least two triangles, so say let this be one shown in red, let this be one shown in green. In each case we find the normal from that surface, and we find this angle. Let this be alpha 1, alpha 2, alpha being the angles between the build direction and the facet normals of these triangles. Now, if alpha is less than this critical angle theta, no supports needed. If alpha is greater than this critical angle theta, supports are needed. Here we found this critical angle to be 120 degrees. So we calculate the angle alpha for the given case. So we're not even required to find it, it's just the criterion. So the cos inverse of the z component of the facet normal in the critical case will be equal to 120 degrees. For all cases where it is below, supports are needed, which is shown here. This is also highlighted for this complex geometry shown here. So all the regions highlighted in yellow are the ones which will require support. Of course, the ones we see here at the bottom require support by default because they are in contact with the build plate. So typically you will have supports on the bottom as well. Say if this is your substrate and this is your geometry, will always have supports here in the case of processes like FDM or powder bed fusion or any other, which make separation from the substrate easier and which preserve the build quality, the surface quality of your build. And also it acts as a sort of machining allowance when you want to separate your part from the substrate using a process, say like Viridium. So now we looked at what are supports when they are needed and how do we calculate when supports may be required for a structure. Once that is done, we aim to generate these supports from the facets, and the mathematical framework for that is illustrated here. So I'll not go through this derivation again. And what we're essentially doing is, this was the case for any generalized build direction, and here is a simplified case for the positive Z build direction. What we're doing is, we are projecting. First, we choose the triangle, which other triangles. So I might as well write it. We choose or we find the triangles with facet normals, making angles with the build direction greater than the critical angle needed, beyond which supports are required. Once such triangles are identified, we project them onto the build plane, such as shown here. And what such a projection will accomplish is that the x and y coordinates of the points will remain the same, whereas the z components will simply be set to 0, as shown here. Also, if we are to go by this paradigm, we can explicitly calculate the volume of the support structures which it will generate. And in this case, it will be summation from 1 to n being the numbers of such triangles which were identified in the previous step, times the volume of the support subtended by each such triangle, which will simply be the area of the triangle times the average height. How we calculate the average height is simply by taking the mean of the heights of the 3 points. So in this case, they will be the z components of the 3 points. So height h1, h2, and h3. This will give us a gross idea. Of course, it's not exact. So yeah, where n is the total number of down-facing facets of the STL file. Down-facing means facets which have facet normals inclined at angles with the build direction larger than the critical angle. AI is the projected area of facet I onto the horizontal slicing fin. HI is the average support height evaluated from the corresponding facet to either the platform or the next intersecting facet, whichever is less. This is another thing we should cover. So, say when you're printing something like, say, the letter E, the bottom face, of course, will have these support structures projected onto the build plate. What about this mid portion here? Clearly, this also requires supports, but will these supports be subtended all the way onto the build plate? No, these supports will actually terminate on the part itself. Similar for this top layer here. So some of it will get onto this intermediate printed layer. The rest will go here. Thus, we should only choose the average support height evaluated from the corresponding facet to either the platform in cases where it goes till the platform or only till the next intersecting facet, whichever is less. Here is another example of a part which may require supports. And here we have regions. So maybe I can highlight it. These support in this region is projected onto the base, whereas in this other region, the supports are only projected onto the part itself, which again becomes critical because when we're removing the supports during post-processing, now you have two surfaces, or in this case, even three surfaces, where there's a chance that the support structure will leave some artifact or remnants and will affect the surface quality of the product. In this case, you have these two surfaces, and there is this small region over here, which though having an overhang, but the overhang is small enough that it does not require any explicit support. Thus, it is called the self-supporting or the self-supported region. And we see a similar example for the geometry of this bunny on the right. So we see how from the ears, the support structures which are generated get subtended onto the body itself, whereas from the other regions, such as from its face or from its tail, the support structures are projected onto the build substrate. This is an example for estimating where support structures might be needed or not. I'll skip this. It has been covered well in the class. Essentially, the idea is that you look at the STL file and judging just by the Z components of the facet normal of each triangle, we should be in a position to comment whether the support structure will be needed or not. So say for a machine and material combination where the critical angle is still 120 degree, we know that for all such facets which have the Z component of the facet normal less than cos 120 degree or less than -0.5, such faces will need supports. So from this code snippet, we see that this facet has the value of the z component less than minus zero point 0.5. Similarly for this one, number 3 and number 4. So all of these four triangles will be needing supports. Whereas for these last two facets, which have their z component of the facet normal exactly equal to minus zero point 0.5, even though they are all in the critical line, for this example, we say that in this case, the support will not be needed because the condition is that the z component of the facet normal should be explicitly less than minus zero point 0.5. Now we found what support structures are, in what cases they may be needed, and how do we generate them. So the second type of support generation happens from the contours. A contour is but the intersection between the part, or should I say the tessellated part, and the slicing planes. Well, these need not always be planes, as we'll see in the upcoming material. But for now, I just say the slicing planes. So whenever you have a part intersecting with the slicing plane, the boundary which comes out is called the contour. And then there are two methods of such support generation. One is containment method, the other is optimal method, as you can tell by the name. The second one is more optimum. Now in containment, the area to be supported is determined by projecting all the contours on a plane and then merging it to get the external support. This big contour is then subtracted from contours at each slide to determine the internal contour for support. So in this case of the human bone, human femur here, you project all of these slices onto the build plane or on z equal to 0, and you come up with this bounding box, which is shown here. And then for each layer, what you do is you subtract the corresponding contour of that layer. Say for this layer here, it may be located somewhere here. And you know that inside this region is where you need to fill with the build material, and in the rest of the region is where the support lies. So you fill it with the support material. However, a little digging into this method reveals that this is not optimum because it might even lead to the generation of supports for facets or in regions where support is not really needed. Thus, we end up depositing more material than needed. This is overcome in the optimal method of support generation, where you have a comparison of the support structure needed for in every pair of slices. So say for nth and n minus 1th slice, you compare the contours and find where the support structure are needed. From the composite contour found from this operation, you compare it again with the n minus 2th slice and so on. And then you finally generate the supports. So here we have the example from the nth slice and the n minus 1th slice. I will just highlight the n minus 1 on a different color. The nth slice in a different color. So say this nth slice clearly larger than the n minus 1th slice, and thus there will be several regions which are unsupported. There is also the region which overlaps with the n minus 1th slice, which will be already supported, and thus supports will be needed in the region highlighted in purple here. The sequential calculations are also shown. So say for n minus 1, n minus 2, n minus 3, and so on. We project the nth slice on the n minus 1th slice, and this is the union. This is there. So subtraction. So n minus 1 h slice. This is the region where the fresh supports will be needed. Just for this slice combination. Now we compare this union of the two slices again with the n minus 2th slice. We observe that this is the region where supports must be deposited, which is shown here. Compare this union again with the next slice and so on. Also illustrated with perhaps a simpler geometry. So again we have several slices, so n minus 1, n minus 2, 3 and so on. And how we decide where supports are needed is we generate the contours. So say assuming this has a rectangular cross section, nothing funny. So for the nth slice, it may be something like this. In the n minus 1th, it'll shorten substantially, and then it'll keep on decreasing, so on. When we superimpose the n slice on the n minus 1th slice, and we look at the top view of the same, this is the nth slice, this is the n minus 1th slice, and we realize that this region is going unsupported. So when we are depositing the n minus 1th layer, we must also be depositing support in this region highlighted in green. If we perform this operation pairwise for the successive slices, we'll be able to find which are the regions which will require supports to be generated to support the upcoming layers. And at the end of such an operation, it can be seen that there will be this zone where supports are to be deposited or generated in anticipation of the coming layers. However, since the support is not utilized in the next immediate layer, these are referred to as stale supports. And there will be this second region where the supports are generated to support or to help with the deposition of the very next layer. Thus, it might be thought that these supports are made or generated in anticipation of the upcoming layers. These are called fresh support and they are immediately used. That is, they support the deposition of the immediate next layer. We also look at a few numericals on calculating the volumes of stale and fresh supports for different geometries. Now, now that we know that how to generate supports when they might be needed, it is a good idea to optimize the part orientation in order to minimize either the cost, which is often the most straightforward method, or to minimize the volume or amount of support needed, or a multi-objective model which can assign weightage to this all of these, either cost or support or some other factor or a combination of them, and then give us a generally optimized model. Each of these have uh, subdivision into other classes of processes. I will not go through these. Professor Kapil has already described them very well. A multi-objective model which can assign different weightages to each of these optimization criteria might be the most appropriate in certain cases. And some examples of the criteria which may be optimized in such a case are shown here. So either we try to maximize the number of surfaces that are perpendicular, thereby saying that they will not need support structures. So it may help to minimize the total volume of support structures to be generated, or we maximize the number of up-facing horizontal surfaces, something similar. We maximize the number of holes with their axes in the build directions. Why we do this is because, say, you have maybe a cylindrical hole in a part. So you're depositing this cuboid, which also has a cylindrical through hole. Now, if this is not perfectly aligned, and assuming your build direction is positive Z, in this case, you will not require any support materials inside this hole because it will be self-supported. Only thing you do is not deposit material in that region in every slice and you're good to go. However, if your build is inclined with respect to the build direction, what will end up happening is to support this internal wall, you will have to deposit support structures inside this hole. And not only will it be tricky to maintain the exact geometry of your build, the removal of these support structures later during post-processing will also lead to poor surface finish on the internal circular surface of the hole, and machining it will require additional cost and effort. Thus, it is worthwhile to maximize the number of holes with their axis in the build direction. Again, we can look to maximize the number of curved cross sections drawn in the horizontal plane. We maximize the area of the base surface for a simple converging diverging section. This makes total sense because then you are totally rid of the need for support structures compared to the inverse configuration where now all of this region is unsupported. It might still not require supports if the critical angle condition is not exceeded, but then just worthwhile to simply maximize the area of the base surface. We minimize the number of sloped surfaces with respect to the build direction. Again, going with the same logic, because in such a case, you would require minimum supports. And then you minimize the number of trapped volumes. Trapped volumes can be especially tricky in processes such as, say, vat photopolymerization or in powder bed fusion, where there is a chance that you end up entrapping some volume of the build material, powder or resin, as the case may be, into this enclosed hollow volume, and then later it becomes simply impossible to extract this material. Thus, this is material wasted, and it also might interfere with the functionality of your part. Let us look at the second set of slides shared for this week. That is on slicing methods again. Here we'll look at direct and indirect slicing, on uniform and adaptive slicing, something we already talked about last week, on horizontal and conformal slicing. This will explain why I mentioned that it's really wrong to say slicing plane. Then we'll look into the uniform slicing of STL files in greater depth for contour determination and organization of contours. And finally, we'll look into adaptive slicing. So, direct slicing is the process where our original geometry is obtained in a suitable format from any CAD software without the use of any intermediate format, and we slice it into our pre-decided by our pre-decided say layer thickness and slicing planes, and end up with an representation of the slice geometry. So if a sphere is sliced by planes, each cross section will have a contour which resembles a circle, as shown in the first case here. In indirect slicing, of course, we start with our original CAD model, but then we approximate it, say, by tessellation using triangles in an STL file. So it's an approximation. And then the representation also becomes approximate. Thus, it involves the conversion of the CAD model to an intermediary format, such as STL, which we already know is the most widely accepted and most popular. We also discussed its strengths in the previous week. And mostly it is used because of its simplicity and the independence from any specific CAD modeling methods. When slicing, the layer thickness or the interplanar gap between two slicing planes becomes important. So you can have either uniform slicing, where the gap between such slicing planes remains constant irrespective of the geometry that you're trying to capture, or the slicing can be adaptive, where based on the geometrical feature of your part, such as this curved arch here, we can modulate the slicing thickness. So in one case, you have slices of uniform thickness, and while they work well for these rectilinear sections, the errors in capturing the curves is really large. Like you're leaving out these regions, for instance. Whereas in the other case, you still work with thicker slices for the rectilinear regions, which saves time, but you have these very thin slices in regions where you want to, say, represent a more complicated geometry. Thus, very simply, uniform slicing is slicing of the part with uniform layer thickness. We do not change the thickness to adapt for the geometry that we are trying to capture. Whereas adaptive slicing is slicing of the part with variable layer thickness across the build direction. Now, the layer shape that is used for slicing may itself be either horizontal, in which case the method is called planar slicing, or it can be a non-conformal shape. You'll see. So for horizontal or planar slicing, we use flat surfaces to slice the object and deposit each layer on a planar pre-built surface. That is a flat surface using 2.5 degrees of freedom. Professor Kapil explained why it's 2.5. So it's 1 degree for the X movement, 1 degree of freedom for the Y movement. And because the Z motion is not continuous but intermittent, we allot it a zero point 0.5 degrees of freedom. That is why it's called 2.5 degrees of freedom process. And this is the most commonly encountered method which we generally see. So we start with a flat substrate or build plate. We, in this case, we are printing a sphere. So say we sliced our sphere using these planes and maintained a uniform thickness. So we end up with these planar layers. And then we may have a subtractive operation in the post-processing part to end up with the desired shape after finishing. However, this need not always be the case, and we need not always slice horizontally. We may also slice radially using a sphere as the surface. So if the surface of the sphere is our slicing geometry and we slice radially, we'll end up with something akin to, say, the layers of an onion or the layers of the cauliflower here. Where there are conformal layers which combine together to slice the part. So conformal slicing actually uses curved surfaces to slice the object and deposit each layer on a non-planar pre-surface using high degrees of freedom. So an example can be when you are trying to deposit, say, a hemispherical dome. Instead of starting with just a flat substrate or build plate, which will require lots of support, we can actually have a hemispherical core on top of this, and then we can start depositing on it layer by layer. So layer 1, layer 2, layer 3, and this is in 3D space. So you'll end up with a hemisphere which will be deposited. And now, based on the type of core that you used, it may be easily removable later or it may be hollow, and you will end up with the desired geometry. So both the slicing geometry as well as the starting or pre-built geometry may be used to suit different applications. In this example also, say the substrate was a non-planar pre-built surface or just a small sphere. Now, we saw how we can slice any given geometry, and for most cases, it is usually planar. Um, Even in most metal-based AM processes, it is still planar, like the ones I work with. But we know the slices, we have the contours, but how do we build the geometry? So I know that, say, for this layer, I know that the contour looks like, say, square, but how high should it be? That is defined by the layer thickness. But is this height compromising with the geometry as we see here? So in the case of hexagon, in case one, we are using a top-bottom approach. So we start at the top, go to the bottom, and we are simply projecting each slice below. So this is the first slice. In the second case, again, we simply project it below the third slice, fourth, and so on. And what we are doing is we are actually under depositing these regions and we are missing out the material. Whereas for the other half, once we have crossed the equator, by simply uh, projecting the sliced contour below onto the next slicing plane, now we are over depositing in these regions. And both are undesirable. If we go the reverse way, we start at the bottom and go up, and we simply, in each case, we project the contour that was sliced upwards onto the next slicing plane. We end up with what is shown here. So at any intermediate layer, say, you have this contour and you are projecting it upwards. Now again, you have cases of both under deposition, where you have missed out material in these regions, and of over deposition. This may be countered in terms of tolerances. So in one case, you have a negative tolerance approach, where you take the exact geometry as your bounding box, and you're always trying to stay within that bounding box. You do not want to deposit any extra material. This may be especially helpful in cases where you do not have any subtractive machining processes at hand, and you would rather be conservative and conserve the material. So this is called the negative tolerance approach. The counter is the positive tolerance approach, where you are over depositing in all cases. And here the geometry of that you're trying to represent is more important. You are willing to deposit a little extra material. You are willing to invest that material and cost, and you're also willing to remove it later during a post-processing step using something, say, like a milling operation. And here the representation or the exactness of the geometry takes precedence. Now, in indirect slicing, we saw how we first represent the exact geometry using an intermediate format such as STL. In STL, we use triangles to tessellate the file, and thus any slicing operation or planar slicing operation will thus include an interaction of these planar slices with the triangles. I would request everyone to stay muted, please, unless you have any questions. Yes. So, thus, what we're trying to look for is actually the interactions between the slicing plane and these triangles into which the geometry has been tessellated. And a general workflow to work out this interaction can be we, of course, have as input the STL file. Then we define the layer thickness D. This layer thickness, as we saw, will be based on whether the slicing is uniform or adaptive. What is the constraint on time? What is the build rate that we're trying to achieve? What is the exactness of geometry that we want, and so on. Then we find the minimum and maximum Z coordinates of the CAD models. For example, here, the south pole will have the minimum Z coordinate, whereas the north pole will have the maximum Z coordinate. Then we start slicing. This is the case for the uniform slicing. So we start slicing and create slices at Zi equals Zi minus 1 plus D. So this is a bottom to top approach. So say you start at the bottom, then you space it by D, and you continue building slices like this unless you have slice the entire geometry. Now we'll sort and group the triangles. We'll work out the triangle plane intersections. We'll also sort the edges of the polygons, then organize the contours and offset the contours if needed. Several scenarios might arise when a plane is intersecting a triangle, and here the plane is represented only by a straight line. The plane, say, goes into and comes out of the surface of the slide. And depending on the case, you might have 2 points of intersection of the plane with the sides of the triangle, or the plane might coincide with one of the vertices and have another point of intersection. It may coincide only with one point and have no other point of intersection, or it may coincide with two vertices. The third vertex may be either above or below the plane. It might also happen that for some such triangles, none of the vertices, or there might be no intersection at all with the triangles, or in cases where the plane of the normal of the plane and the normal of the triangles are parallel, and the triangle actually lies in the plane of the slicing plane. All three vertices are coincident. Depending on the case that we encounter, our action will be different. So in some cases, we record the intersecting points. In other cases, we record both the intersecting point and the vertices. Some cases might require us to do nothing because the points are already recorded in our STL file. If there is no intersection again, we do nothing, and so on. However, the general formulation of such a case is shown here, where the slicing plane actually intersects our triangle, the sides of our triangle at 2 points, say P1 and P2, and each of these points has to be found out. We'll also do an example based on this. The way we do this is we find the equation of the line AB in 3D space. It will be x minus x1 by x2 minus x1 equals y minus y1 by y2 minus y1 equals z minus z1 by z2 minus z1 equals some parameter t. In 2D space or on a plane, of course, we know that this parameter is just the slope. Then we compute this parameter by the intersection of the line z equals zi and the line AB. Given that the value of zi is already known to us, we know the height of the slicing plane. We can find this parameter t. Once this parameter is found, we can back substitute it and find the x and y coordinates of the points. The z coordinate, of course, will be by default equal to the height of the slicing plane, as is well known. Again, once the edges of the triangles are found, they must also be sorted, and the sorting algorithm is defined here. We'll do the example just to see how it goes. So we want to form a matrix of this type. Here you have for each edge you have x1 of point 0.1 and y1 of point 0.1. You have x2 of point 0.1 and y2 of sorry of edge 1. So the x and y coordinates of each of the vertices of the edges, and you want to have them to form a closed contour such as shown here. How do we accomplish it? The first edge is taken as is, so you have 1 1 and the second point 1 2. Now we try to match the second point with the first point of the remaining. So we look at these. Does 1 2 match with 2 3? No. 2 3 again and 5 4? No. So it is not matching with the first point of any of the edges. So now we try to match it with the second point of the edges. Does 1 2 match with 5 4? No. But it matches with edge 3. So this was edge 1. Now edge 3. Now we flip it. So P2 becomes point 0.1. We have 1 2 and then 2 3. Again we try to match 2 3 with the remaining first points. So it matches with edge 2. So you have edge 2 here. And we don't even need to flip it. So it is 2 3 and 5 4. So and at last we compare it with the first point of edge 4, and we see that it matches and we do not have to flip edge 4 either. So here we have 5 4 and 1 1. And as our requirement was to make a closed contour, the last two entries, that is x2 and y2 here, should match with the first two entries x1 and y1, and they do. This signifies that the contour is closed. Of course, for any valid solid, when sliced by an slicing plane, will never end up with the open contour, because that will signify that some triangle is missing, which will lead to an error in our STL file. Once the contours are identified, we should also be in a position to organize them and to know, as is the case here, say we have several contours, inside which contours is material present. Are there any contours which are hollow? Which contours are contained by other contours? Are there any contours which are unrelated, such as 1 and 8 here? And how to have an easy way to identify these relationships. This is accomplished by this relationship matrix, which is shown here. Just a second. Yeah. This is shown by the relationship matrix here. And the rules are that we look at two contours, I and j, and the relationship value is defined as plus 1 if contour I contains contour j, minus 1 if contour I is contained in contour j, 0 if they are separated, and plus 2 if I equals j. The solution for both are given. Okay, let us still do this. It will be illustrative. So for the first row, I is equal to j, so this will be plus 2. And we can see that this will be true for all the diagonal elements. So we populate that first. This simply signifies that the row and column values are equal. Now we are looking at R12. Now contour 1 contains contour 2. So this is plus 1. Contour 1 contains contour 3 again, 4, 5 and 6, 7. 8 and 9 are 0 because they are separated. Now we look for contour 2, 1. So 2 is contained in contour 1, so this will be minus 1. Contain 3 is contained in 2, so plus 1. 4 is contained in 2, so plus 1. 5 into 6 into 7 is separate, 8 is separate, 9 is separate. 3 is contained in contour 1, so this will be minus 1. 3 is contained in contours 2, so minus 1 again. 3 contains contour 4, so 1. 3 contains 5 and 6 as well. 3 is separate from 7, 8 and 9. Now contour 4 is contained in contour 1, so minus 1. 4 is also contained in 2 and 3. 4 is separate from 5, 6, 7, 8 and 9. Contour 5 is contained in contour 1, also in contour 2 and contour 3. However, it is separate from contour 4. Contour 5 contains contour 6, is separate from 7, 8 and 9. Contour 6 is contained in 1, in 2, in 3. It is separate from 4 but is contained in 5. It is separate from 7, 8 and 9. Contour 7 is contained in contour 1 and 2 but separate from 3, 4, 5 and 6. Also 8 and 9. Contour 8 is not, it is separate from 1, 2, 3, 4, 5, 6, 7, but it does contain 9, and contour 9 is separate from all of them and is simply contained in contour 8. Thus, what we observe is the relationship matrix that we obtain is actually skew symmetric. And here is also a hierarchical diagram representing this relationship. So in the first level, we assume there is a virtual exterior contour which contains all the contours, and that gives us the relation tree. So this virtual contour has these two contours 1 and 8. One contains 2, 2 contains 3 and 7, 3 contains 4 and 5, 5 contains 6, 8 contains 9. And the way we go about is all external contours are traversed in a counterclockwise direction, and all internal contours are traversed in a clockwise direction. How do we determine which is external and internal? So if the number of times -1 occurs in this relationship matrix is odd, then it is an interior contour, and if it is even, then the contour is exterior. So 1 is an exterior contour, so it has material on the inside of it, highlighted in red. 2 has odd number of -1, so it is an interior contour and material on the has a material on the outside of it. Similarly for 3, 3 is an exterior contour, 4 is an interior contour, 5 is an interior, 6 is an exterior, 7 is an exterior contour, and so on. We see some other cases where adaptive slicing is helpful. One is to preserve the peak features. So here we see that the original geometry had certain sharp features that should have been preserved at this point, this point, this point, and so on. But because of the choice of slicing height, they could not be preserved. Whereas if we use an adaptive slicing method, we are able to preserve these peak features. Also this. Second is to reduce the cusp height. Thus here you have this curved surface and the error between the actual geometry and its sliced representation measured by cusp height can be reduced if we instead opt for finer slices. And it can be used to eliminate the support structures altogether, as Professor Kapil has demonstrated. There's also this very illustrative example which comes with a full solution. So I will not iterate it again. We'll just break for a short while and then we'll continue solving some more illustrative examples. So let's meet in around 5 minutes or so. Hi and welcome back. So, in the meantime, a question had been posed in the chat. What if the rotation is clockwise? Will there be any change in the rotation matrix? So, just to recap, the rotation matrices that were discussed in class and that we looked at in the slides are defined for counterclockwise rotation. That is the typical, say, sense of a positive rotation. But what if this rotation is counterclockwise? Will that bring any change? And the way to look at it is, say, about the z-axis, you have a rotation by theta. This can also be construed as a counterclockwise rotation over the same axis by an angle of 2 pi minus theta, or perhaps even easier to visualize in two dimensions. So, say, we have the x and y axes. For the z axis, you rotated a point by some angle theta to reach this final configuration here. This is equivalent to an anti-clockwise rotation of 2 pi minus theta. So the only change that will occur is in all of these coefficient matrices, which are for counterclockwise rotation by theta, you substitute theta with 2 pi minus theta in case of a clockwise rotation. Everything else remains the same. Thank you, Moses, for posing that question. It was really insightful of you. So now let us look at a few illustrative examples. The first one, again dealing with rotation. So you have a few lines of triangle from the code of an STL file, and you have a sequence of rotations. Triangle is rotated in 90-degree counterclockwise about x, and 90-degree counterclockwise about y, and 90-degree counterclockwise about z. What are the new coordinates of the triangle? We already discussed the derivation of this in great depth. We know that we have to do this pointwise, and each new point, say P1 new, will be some matrix multiplied form of the previous point. So we have the original P1. You start with uh, rotation about the x-axis, then y-axis, and then z-axis, and you end up with the new point. So also you have the angles given here. So theta x is pi by 2, theta y is pi by 2, and theta z is pi by 2 as well. Maybe we can do this for one point. So given that theta x is pi by 2, we find the rotation matrix r theta x. I'm just reproducing the formula from the slides. So it is 1 0 0 0 cos theta x minus sine theta x and 0 sine theta x cos theta x. Given the value of theta x equals pi by 2, this will actually turn out to be 1 0 0 0 0 minus 1 and 0 1 and 0. Similarly, you may find r theta y, which is cos theta y 0 sine theta y 0 1 0 and minus sine theta y 0 and cos theta y. With the value of theta y equals to pi by 2, this will be 0, 0, 1, 0, 1, 0, minus 1, 0, 0. The matrix is also given here. And similarly for our theta z, you have 0, minus 1, 0, 1, 0, 0, and 0, 0, 1. Now let us rotate one point. Let it be, say, this point here, P1. So originally, P1 is equal to 2, 1, 0. R theta x times P1 is actually the operation 1, 0, 0, 0, 0, minus 1, 0, 1, 0 times 2, 1, 0. This is 3 cross 3, this is 3 cross 1, so the product will be 3 cross 1, and we have 2, 2 into 1 plus 1 into 0 plus 0 into 0, 1 into 2 into 0 plus 1 into 0 minus 1 into 0, so 0, and 2 into 0 plus 1 into 1 plus 0 into 0, 2, 0, 1. We next multiply this with our theta y. This is actually the operation 0, 0, 1, 0, 1, 0 minus 1, 0, 0 times this, which we obtained in the previous step, 2, 0, 1. Again, this will be a 3 cross 1 matrix. So you have 2 into 0 plus 0 into 0 plus 1 into 1, 2 into 0 plus 0 into 1 plus 0 into 1. So 0. 2 into minus 1 plus 0 into 0 plus 1 into 0. For the final step, you have r theta z times r theta y times r theta x times p1, which is but the operation 0 minus 1 0 1 0 0 0 0 1 times this, which you obtained in the previous step. So 1 0 minus 2, this will come out to be 1 into 0 plus minus 1 into 0 plus minus 2 into 0 is 0. 1 into 1 plus 0 into 0 minus 2 into 0, and 1 into 0 plus 0 into 0 minus 2. So P1, sorry, P1 new is equal to 0, 1 minus 2. This exercise can be repeated for the other points, and I've also enclosed the answer for you to verify. Of course, an easier way to do this would be in some software such as MATLAB or Mathematica, and we will have the reoriented triangle. The second question has data from the same STL file. So the emphasis is not on the data, but on the algorithm on how to solve this problem. And now we have to find the new unit vector corresponding to the new facet normal. So say we originally started with this triangle. Say it had the points P1, P2, P3, and it had a normal, say N1 hat, which originally pointed in some direction. Now, after the set of rotations that we carried out in the previous example, the triangle may have been reoriented. So say this might now be P1 new, P2 new, and P3 new. And the facet normal might also have changed direction. Now we have to find this unit vector corresponding to this new facet normal. So let us do that. We already have the new vertices, so I will just write it. P1 new is 0, 1, minus 2. P2 new is 1, 3, minus 4. And P3 new is minus 4, 2, and 2. In the previous week, we already discussed how to find the facet normal of a triangle. So if this is our triangle, P1 new, P2 new, and P3 new, we can use the vector product or the cross product to find the facet normal. So say the vector P1, P2 can be denoted by A, and the vector P2, P3 can be denoted by B. A vector thus will be nothing but 1, 3, minus 4, minus 0, 1, minus 2, which will come out to be 1 minus 0 is 1, 3 minus 1 is 2, minus 4 plus 2 is minus 2, and B vector may be computed as P3 minus P2, so minus 4, 2, 2, minus 1, 3, minus 4, so minus 4 minus 1 is minus 5, 2 minus 3 is minus 1, and 2 minus minus 4 is 6. Now we can calculate the cross product, which is simply the determinant of ijk 1, 2, minus 2, and minus 5, minus 1, and 6. I will expand along the first row, but you can perform any equivalent operation. So 6 into 2, 12, minus 2 into minus 2, or minus 2 into minus 1, 2, minus j hat into 1 into 6, 6, minus 5 into minus 2 is 10, plus k hat into 1 into minus 1 is minus 1, minus 5 into 2 is minus 10, so plus 10, which comes out to be 10 I hat plus 4 j hat plus 9 k hat. Now a cross b is a vector normal to both a and b, but it is not the unit normal. To find the unit normal, we simply divide it by the norm of a cross b, which in this case is 10 square plus 4 square plus 9 square, or 100 plus 16 plus 81 is 181 plus 191 plus 197. And this our new unit normal is a cross b by norm of a cross b equal to 10 I hat plus 4 j hat plus 9 k hat by under root of 197. This is the new facet normal after rotation. Again, we have the same triangle, but in this case, the triangle is translated plus 2 unit along the x-axis, plus 3 unit along the y-axis, and then plus 4 unit along the z-axis. And we are to find the unit vector corresponding to the new facet normal. Now, this may look like a lot of work, but the funny thing is, all we should remember is that any rotation may change the unit normal, but in this case we are dealing with pure translation. Translation alone will not change the unit normal because you are simply moving any body parallel to itself along any of the three directions. So we can save a lot of time and effort by not recalculating the unit normal and say that it is exactly as we calculated in the previous step. So the unit normal is still oriented along this vector. In the fourth question, we are given that in an AM process, the triangles of the STL file with facet normal at an angle more than 120 degrees from the build direction require a support structure. A few lines of a triangle from this code of the ASCII format are given here. Does this triangle require a support structure if the build direction is positive z? Now we determined the requirement of support structures by finding the angle between the facet normal and the build direction. And if this angle turned out to be greater than the critical angle for that machine and material combination, it was determined that support structures may indeed be needed. So first, we must find the unit normal. If you look carefully, these points are actually the points obtained after rotating our original triangle of question 1, 0, 1, 0, minus 2, 1, 3, minus 4, and minus 4, 2, 2. And we have already computed the facet normal corresponding to this reoriented triangle, which turned out to be 10 plus 4 plus 9, so 10 plus 4 and plus 9 by under root of 197. We already have the unit normal for this facet. The build direction is specified as plus z. Now we must find the angle between the build direction and this facet normal. So angle between the unit normal of the facet and the build direction, both are vectors, and the way we find angles between vectors is usually by using the scalar product or the dot product. So it's simply into vector into hat dot k hat. K hat because the build direction is along positive z, and in a usual representation this will be equal to norm of n2 hat times norm of k hat times cos theta, theta being the angle enclosed between these two vectors. Given that the components of N2 are known to us, we can also perform the dot product component wise. Hi Ranjan, I see your raised hand. I'll just take your question after we do this question. So here we have 10i hat plus 4j hat plus 9k hat by under root 197 dot k equals, given that N2 hat is a unit vector, its magnitude is 1, same for k hat, and only cos theta remains. Now I dot k is 0, j dot k is 0, k dot k is 1, so we have 9 by under root 197 equal to cos theta. Now, do we need to explicitly calculate theta in this case? I mean, I will calculate it. So theta is cos inverse of 9 by under root 197, which turns out to be 0.8747 radians or 50.1169 degrees. And based on this, we can say that clearly this is, well, 50.1169 degrees is clearly less than 120 degrees. And thus the supports are not needed. But we did not even need to calculate this because we saw that the cos theta was positive. A positive cos is in the first quarter. So we know that this is clearly less than 90 and this is clearly less than 120 degrees. Also, if you remember for the lectures, for the critical angle equal to 120 degrees, cos of 120 degree was minus zero point 0.5. There's any value of this cos theta which was greater than negative zero point 0.5 would imply that the angle enclosed or the angle between the unit normal and the build direction was smaller than 120 degrees and thus the support structures would not have been needed. So even qualitatively, we can comment that the supports are not needed. Ranjan, you have a question? Ranjan, could you unmute and pose your question? Okay, Ranjan might not be here with us right now, but we'll take his question later if time permits. Let us move on to the next question. Here we are given a complicated geometry which is to be built along the positive z direction. It is to be fabricated by an additive manufacturing process. Now, considering the optimal method of support generation from contours, and given the ratio RC by RS equal to 4, where RC and RS are illustrated here. RC is this dimension, and RS is simply the radius of the hemisphere. Given this information, we are to find the ratio of volume of the stale and the fresh supports. Let us do that. Okay, maybe we can start on the next page. From the examples that we have seen, let us try to judge qualitatively where the regions for the fresh and stale supports will be. Clearly, the supports will only be needed till this plane. Above it, no supports are needed because the structure is self-supporting. And say this is the substrate. Of course, there will be some small support here also, but for the purpose of this question, it can be ignored. And supports will be required for all of these regions. But as we already saw, the support in this region will be stale because we will be generating this support from the very first slice itself, but it will not be immediately useful. And the actual overhanging part that the support is being built for will only be encountered at the very end near the equator. Similar for this side. And we are only showing a cross-sectional view. This is in 3D space. So what we're really talking about is a volume of stale support and a volume of fresh support. So let us now calculate these volumes. So starting first with the volume of fresh support. Now that region looks something like this. So in fact, not even- something like this with the bottom touching this square. And this is a hemisphere. Clearly my sketching is very bad. And what we have is a cylinder and a hemisphere. Let us try to calculate it. The dimensions are already given to us. So this half distance is RC. The height is also RC. Clearly they are not equal from my sketch. Then this sketch is not to scale either. And this volume of fresh support equals volume of the cylinder. So pi RC square H, which is also RC, minus the volume of the hemisphere, which is half 4 by 3 pi RC cube, which turns out to be pi RC cube minus 2/3 pi RC cube, which is 1/3 pi RC cube. Now we have to find the volume of the steel support. For the region of steel support, we can approximate it by these two cylinders or a hollow cylinder, and the dimensions are given to us. This distance is RC. This distance, oh, sorry, guess I interchange RC and RS. So all of these are in fact RS, or the radius of the sphere. This distance is RS, and this one is RC. And we can compute this volume as the difference between the volume of the inner and the outer cylinder. So the outer cylinder will have a volume pi. This height is also RS pi RC square times the height RS minus the volume of the inner cylinder. Maybe I should also write it. It may be of use later. Now the outer cylinder minus the volume of inner cylinder, which is equal to pi RC square RS minus pi RS square times RS, which is equal to pi RS times RC square minus RS square. Now, we have to find the ratio of volume of the stale and fresh support Vs by Vf. Vs by Vf, stale support is pi Rs times RC square minus RS square by Vf, which is one third pi Rs cube. Pi gets cancelled out. One RS gets cancelled out. The 3 goes on top. So you have 3 RC square minus RS square by RS square. If you take this RS square inside the bracket, you have 3 times RC by RS whole square minus 1. Now this value is already given to you. RC by RS is equal to 4. Given this information, Vs by Va then equals 3 times 4 square minus 1 or 3 times 16 minus 1, 45. Thus, the volume of steel support is 45 times the volume of the fresh support. Based on different values of the ratio of RC and RS, you'll end up with different ratios here. The sixth question, again asking us to just give a qualitative answer by inspecting the values. And you have 3 facet normals given to you. The build direction is plus Z and the base is at Z equal to 0. Which of these 3 facet normals would you recommend to examine for the requirement of the support structure? Now, just to recall, facet normals which have the Z components positive do not require support structures. If the build direction is along plus Z, for other arbitrary build direction, we will have to check for the relationships. Facet normals with Z components which are negative may require support structures based on how big or how large the inclination is. For the first facet normal, we see that these are nx, ny, and nz. For the first facet normal, we see that nz is less than 0. Thus, we should recommend it for checking whether the support structure is needed or not. For the second facet normal again, nz is less than 0, and thus even this should be recommended. For the third case, z is greater than 0. This clearly implies that support structures are not needed. Thus, we should not recommend this triangle for uh, the examination of need for any support structures. There is one remaining question which okay, I'll cover right now because it might help you with your assignments. So, few lines of a triangle from the code of ASCII format are given here. You have to find the intersection point or points given that there may be more than one or none at all, between this triangle and the slicing plane z equals 2. So the generic formulation has been reproduced here from Professor Kapil's slides. And for the generic formulation, we see that there will be 2 points of intersection with the triangle, and the way to do it is we first compute the parameter t, then we find the points. Now, for each point of intersection, say P1 and P2, assuming 2 points of intersection, P1 and P2, the parameter T will take on different values. So let us do it for the first case, where you have P1, let it be the point of intersection of Z equals to 2, and the line AB, say where A has the coordinates x1, y1, z1, B has x2, y2, z2, and C will have x3, y3, and z3. So A has the coordinates 2, 1, 0, and B has 4, 3, 1. Let us find the parameter t. T is equal to zi, which is equal to 2, minus z1, which is 0, by z2, which is 1, minus z1, 0, or 2. xp is equal to x1, which is 2, plus the parameter t into x2, which is 4, minus x1, which is 2, which is equal to 6. Did I do something wrong? Okay, 0. Okay, so this we found an interesting case because of the z coordinates 0 and 1. This line will not be intersected by the plane. So we'll have to check for its intersection with the other two lines. So this line AB will not be intersected by the plane z equals to. So we now go for the second case where intersection between z equals to 2 and the line BC, where B has the coordinates 4, 3, 1 and C has the coordinates minus 2, 2, 4. We calculate the parameter t, which is zi minus z1, so 2 minus z1 by z2 minus z1, or 4 minus 1, this is equal to 1/3, and then xp is equal to x1 plus t into x2 minus x1 equal to minus 6 minus 2 to yp is equal to y2 y1 plus t into y2 minus y1 equal to 3 minus 1 third 8 by 3 zp equal to z1 plus t into z2 minus z1 equal to 2, which is obvious because this point also lies on the plane z equals 2. Therefore, P1 has the coordinates 2, 8 by 3 and 2. Now we must find the second point of intersection, P2, which is the intersection between z equals 2 and look at AB, BC, then C. Of course, C has the coordinates minus 2, 2, 4, and A has the coordinates 2, 1, 0. Again, we start first by finding the parameter T, which is Zi minus Z1 by Z2 minus Z1. This is minus 2 by minus 4 or half. XP is equal to X1 plus the parameter T times X2 minus X1. So 4 times of X2 minus 2, so this is 0. By T equals Y1 plus T times Y2 minus Y1. This is 2 minus 1, 1 minus 2 is minus 1, 2 minus half is 3 by 2. Zp is Z1 plus T into Z2 minus Z1. This is 4 minus 2 is 2, which is the same as Z equals 2. Therefore, the second point of intersection has a coordinate 0, 3 by 2 and 2. And this is all that was asked. So, therefore, the two points of intersection are P1 2 8 by 3 2 and P2 0 3 by 2 and 2. That's all the illustrative examples I had for today. Sorry, I exceeded our meeting time again. Thank you for your doubts. Someone had raised their hands, but they did not pose the question again. So we'll take it up in the next class. Thanks for tuning in. Um, see you next week. Thanks.